Hi, I'm Professor Shiva Panchakshari. In this video, I'm going to explain the derivation of Ampere's law in point form or a differential form. That means I'm going to give an expression for curl of magnetic field at a point. So we need the differential form of Ampere's law. But we have already using the integral form of Ampere's law, which is given by integration of h over a closed path is equal to the current enclosed by the closed path. That means if we have a closed path, say C, then evaluation of magnetic field H on this closed path is equal to the total current enclosed by the path. That means total current present within the closed path. This is what is Ampere's law in integral form. This integral form is very useful to find H over a closed path. But here is a problem, that is computational complexity of this integration. So integrating H along with the path or the path of different shapes will make this mathematics very complex. It is very difficult to handle that much of mathematics. So that's why Ampere's law is used in integral form only to symmetrical cases. So that means the magnetic field and the closed path both should be symmetric with respect to each other. Then only the evaluation of this integration of H is possible. When H and dl are symmetric, H becomes constant over the integral path and can be taken out, and the integration decreases, complexity decreases. So that's why Ampere's law in integral form has limited applications. You cannot apply everywhere. Also in electromagnetics, we want equations to explain any concept or evaluation of any quantity at a particular point rather than over a surface or over a closed path. So that's why we always would like to have very important equations in point forms or differential forms so that we can address some quantity at a particular point. Here also we make an attempt to derive the Ampere's law in differential form. So for that we have to make some preparations. First one, we have to make something so that H remains constant on the closed path. So what I suggest is that choose a very small closed path, so that H remains constant on the closed path. Our variations in H for the closed paths are negligible. So that's why we start this derivation with a very small closed path enclosing a very small area, let us say delta S. Then H becomes constant, H can be taken out. Then to handle this dot, that is dot product, which is having cos theta there, theta should be chosen either 0 degree or 90 degree. That means the direction of the magnetic field and the direction of the path dl, both should be either parallel or normal to each other. When they are parallel, theta is 0. When they are normal, theta is 90 degree. So the complexity reduces. So while choosing the closed path, we have to take care of these aspects to reduce the complexity of the problem. So I'm going to derive this law in rectangular coordinate system. So I'm choosing a rectangular path as shown in the diagram. See here, I've chosen a rectangle of area, say delta S. One side I have taken the length as delta x. This is parallel to x-axis. Other side, delta y parallel to y-axis. No side is parallel to z-axis because this rectangle is perpendicular to z-axis and located, let us say, at some plane, say z is equal to constant plane. So z is constant over the entire rectangular path. At the same time, I have assumed that the magnetic field is H naught at the midpoint of the rectangular path. H can have three components, x, y, z components in rectangular coordinate system. We shall assume that we know all these values at the midpoint of the rectangular path. And the area is incremental area. And the variations of the magnetic field on this path are very negligible. So we can take them as constants. So we shall proceed further now. So end of the day, what we do here is first we'll evaluate h dot dl by choosing one path at a time. That means from 1 to 2 we choose the path, then evaluate this integral, then from 2 to 3, 3 to 4, 4 to 1. Then finally we add all the equations to get the final relation. Right. And later after that, we apply the limit to this surface delta S to shrink it to 0. Then this integration or the closed path will be divided by the surface. Now the quantity becomes circulation per unit area. Circulation density we can call it. After applying the limit delta S tends to 0, this equation becomes curl of H. I've explained the concept of curl in detail in my previous video, which was labeled as MF1, magnetic field 1. So these equations are discussed in detail there. So at present, you please remember that the integration of a magnetic field or a closed path, which can also be called as circulation of the field H, when it is divided by the surface, it's called circulation density. When the surface shrinks to 0, it represents a point representation. That time we can define it as a curl. So let us proceed now with the circulation. So the incremental area is taken as delta S. It's given by delta X into delta Y. And I have defined the magnetic field at midpoint of the rectangular path, which has assumed that all the three components are present in the magnetic field. Now we shall start with Ampere's law in integral form, which is given by line integral, which is given by the line integral of H over the closed path C. I have a closed path C here given in the picture. I would like to split this closed path C into 4 different straight line paths, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And we shall evaluate the integration. So I have divided. Okay, you just look at this equation here. I have splitted the closed path integration of H as 4 different integrals. First one is the evaluation or the path from 1 to 2, that is H dot dy ay. Take this path 1 to 2. Okay, the differential length dl here, differential length dl can be taken as dy, because this direction is taken as y-axis and this direction is taken as x-axis. This path 1 to 2 is exactly parallel to y-axis. Therefore, the length of this differential path can be taken as dy. And look at the arrow, that is this one. It is acting in the positive direction of the y. That's why the vector dl, differential displacement, can be taken as d by a cap y. So that is what we have put it here. Similarly, for the path 2 to 3, we can choose a differential length, that is dl, equal to, and this line 2 to 3 is parallel to x-axis, but oriented in the opposite direction of the x-axis. That's why the magnitude of this displacement is dx, direction is minus a cap x. That is was used here. Similarly, for part 3 to 4, the dl goes this way, and this is parallel to, once again, to y-axis, but opposite to y-axis. That's why it is going to be minus dy ay. The last path, which is exactly oriented in the positive direction of the h, that's why it is dx ax. So the closed loop integral of h is split into 4 open integrations over straight line paths, and the total value is equal to I according to the integral form of Ampere's law. So in the next step, what we have to do here itself we shall write all of them. The paths are taken care of, fine. What about h? H has all the 3 components, and as I said, h can be taken as h naught at the midpoint, which has 3 components, hxo, hyo, and hzo, az. And all these 3 components are defined for the center point. But we want h over path 1 to 2 because this first integral is performed over path from 1 to 2. So we have to find h on the path 1 to 2, right? See the arrow mark and see the dot product here. When this h, which is defined at O, can also be defined on the path 1 to 2 as h12. h12. So we can write h12 as h x12 ax h12, sorry, hy12 ay hy12 az. Same way as h0, we can define h12 over the path 12 because the magnetic field h changes from point to point, so it will not be same everywhere. So now with this h12, if you perform dot product with dy ay, then ax dot ay is 0, ay dot ay is 1, az dot ay is 0. That means only y component of the h will be obtained after the dot product. So that is why after the dot product we will be having only hy12. We'll be having only hy12 component on this path 1 to 2. Other 2 components become 0 because of the dot product. Similarly, after performing integration over 2 to 3, which is oriented in x direction, we will be having h here as, you can predict easily, x component will be present over here. It's going to be x2 2 3. Similarly here, hy3 4, hx 4 1. So like that, we can designate the components of the magnetic field present over each path. Okay, 1 to 2 parallel to y-axis, so it can have only y component because ay dot ay is 1, other components are 0. Similarly, over 2 to 3, you can have only x component, but this value will be designated as hx23 instead of hx12. Hx12 is over path 12, which will be 0. Similarly, the corresponding components are identified, and we get another equation finally with the changes. Look at this one. Over the path 1, 2, we have y component, 2 to 3, x component, 3 to 4, y component, and 4 to 1, x component. See the polarity, it is minus. The minus come from this minus dx ax minus dy ay. So it's time to find out what is hy12. How to find hy12? First of all, is it a constant? Yes. As I said in the beginning, Ampere's law is applicable only for symmetric considerations or symmetric applications where h should remain constant over the path. If h is not constant, then it leads to a very high complexity of the mathematics. We do not consider such cases at all here. Because of that, h should be constant over this one. I'll give one more reasons why h should be constant, because we have chosen a closed path enclosing smaller area, incremental area. We have taken incremental area intentionally to make the h constant over each side of the rectangle. So that's why hy12, hx23, hy34, h4, all these are constants. They can be taken out of the integrations. So we need to integrate only the differential length. Now, what is the integration of dy from 1 to 2? If you go back to the diagram and see from path 1 to 2, if you integrate dy, you'll get total value. The total value is delta y. That's going to be delta y. So after integration of dy, we'll get delta y, the total length of the side. Integration gives total value. So the total length of the side 1, 2 is delta y. It's given here. Taken. Similarly, others also. H values are taken as constant, 2 to 3 delta x versus delta y, delta x. Correspondingly, h components of h are taken out of the integration and differential lengths are integrated. We get incremental lengths, the total lengths of the corresponding sides. So now it's time to find magnetic field H. The length of the each side is calculated already. So what is Hy12? We shall work out that. If you reconsider the diagram, the rectangular path, what I had taken, this one. This side is designated as 1 to 2. Now, the total length of this side is delta y. The magnetic field on this side is Hy12. How to find Hy12? But we know here HO, which has all the components x, y, z. Among them, only y component is required for us on this 1, 2. So that's why the y component of magnetic field at the midpoint is HYO. This HYO is acting in this direction. That is y direction. That's why it is called y component. And this is parallel to this path. And this HYO changes itself to become HY12. Are you getting my point? HY12 is produced by HYO. So HYO and HY12 are different from each other. Let us assume that we know HYO. Then what is the value of HY12? That depends upon how much this HY0 changes while moving from the midpoint to this side 1, 2. While traveling this much of distance, how much changes it undergo? That change, if you consider, you will get this value Hy12. So first of all, what is this distance? If you take this side, this is delta x, and this is being midpoint, and this length is delta x by 2. So that means HYO undergo some change in its value while traveling a distance of delta y by undergoing a change. So that's why I can suggest an equation for HY12 as its initial value HYO at the midpoint, and we have to write here the change in HYO to become HY12. So this y component of h at the midpoint is changing while traveling this distance delta x by 2 in the direction of x. Look at this arrow mark. This is changing with respect to x. So we can represent change of h with respect to x as dou hy by dou x. This is a partial change because h also changes with respect to xy at different points. So that's why dou hy by dou x indicates that change in magnetic field with respect to change in distance. So we want only change in magnetic field, dou h we want. So change in distance, we know that one. What is the change in distance from HYO to HY2 is delta x by 2. That's why if you multiply this quantity by delta x by 2, delta x by 2 the total change in distance. When you multiply with this one, change in distance correspondingly cancelled out, you will get change in total change in y. So when this change is applied to HYO, you will get HY12. So in a summary, the magnetic field y component, which was HYO at the midpoint, becomes HY12 on the side 12 while undergoing this much of change. So first quantity gives rate of change of y component of h with respect to x into the corresponding change in distance. So these two terms are representing actually the first two terms of Taylor series, which is used in mathematics to express the quantities which are changing by smaller values. Here h is changing by smaller values. So we took the help of Taylor series to write this equation. Similarly, we can write other quantities of h also. So first point to be noted is initial value HYO, fine. Second term is rate of change of h with respect to x. Delta x by 2, that is exactly acting in positive x direction. So that's why it's a positive quantity. We can put this equation to HY12. Similarly, if you want to understand another quantity, that is over 2 to 3, what you want to find is hx to 3. As usual, you have to take, see the x component is only required on 2 to 3. That's why the x component at the midpoint is hxo. This hxo will change to hx23 after undergoing a change over this distance. So this distance half of this line, and this total length is delta y. So this is delta y by 2. Look at the arrow mark. This arrow mark is towards positive y-axis. So the change in delta y by 2 is also positive. So keeping this concept in mind, I can write hx23 as the initial value hxo plus change in x component of h with respect to y, because the change is happening over the length of delta y by 2. It's happening with respect to y. Hx is changing with respect to y into the total change here is delta y by 2. That is in positive y direction. So this makes hx23. Similarly, we can predict hy34. So this is hy34, that is starting with your Y component we have to consider here as H5O that is undergoing change in this direction. What is the direction here? It is this is opposite to x-axis. Positive axis this is opposite to x-axis. So the corresponding change over is minus delta x by 2. The minus indicates distance is taken opposite to the positive axis. So this is to be considered. So another equation in the same way for Hy 34 will be HYO plus what is that one? Dou Hy by dou x. That is change happens in x direction, but negative. So we have to introduce negative sign there for this. Likewise, the rates are always taken as positive, irrespective of the direction, but the change in distance comes with direction because magnetic field is a vector. So every term in the equation of H is a vector. So everything is having a direction. So likewise, we can write other quantity also. Let me take the complete equation similarly. So we have the equation accordingly. So here each component is represented HYO dou Hy by dou x. So same equations, 3. Fourth one is I have left you. You can only analyze. Okay. So what is that equation is? That is to be taken for this path. This is opposite to y-axis. So it's going to be minus delta y by 2. Minus delta y by 2. Because the distance is happening in negative direction. So that is taken care of here. So look at this one. The 4 terms are introduced here into this closed loop line integral. And we have to simplify this equation now. Carefully observe here. HYO, which will be multiplied later with delta y. And here is one more HYO, which is also multiplying delta y. But it is having a negative sign here, where this one is positive. So that's why when added, both get cancelled. That means these two are getting cancelled after summing up. Similarly, HXO with delta x, HXO with delta x. One negative, one positive. So these are also getting cancelled. So other terms, you carefully observe. Look at this term. Dou Hy by dou x. Is there any dou Hy by dou x? It is there here. Both are same. Delta x by 2 into delta y. Delta x by 2 into delta y. One is plus, one is minus. But here is one more minus here. So minus into minus plus. So that means these two are getting added up. Similarly, same thing happens. These two are getting added up. This is minus into plus minus. This is already minus. So both will be getting added. So first term and third term are adding up. Second and fourth terms are adding up. First and third are positive. Second, third are negative. So on simplification, we are having this equation. Right. So dou Hy by dou x. Because after adding, the first and the third term becomes 2 times into 2. So denominator 2 gets cancelled out. So we have this equation. So now delta x, delta y becomes common factor. It is taken out. Right. This is the area. So the very first term in this equation is circulation of H. That is given by the rest of the equation. Last term is current I. So we know that from the definition of the curl, which is the circulation per unit area. Circulation per unit area. So we would like to introduce area term into the denominator. That's why I would like to divide this complete equation by the area delta x into delta y. So the first term is divided. In the second term, Already area is there in numerator, that gets cancelled out last one. So the middle term is independent of area. Only first and last are dependent, right? So now we can consider some definitions at this point of time. What is that one? As I said, we have a definition of curl H, which is discussed in the previous video detail, which is given by circulation of H or integral of H over closed path divided by area delta S as the area tends to 0. This is the definition of the curl H. And look at the consequences. Curl H is a vector operation, but right side is a dot product, which is a scalar operation. So that's why the left side is not having the vector form. It's going to be a component of the vector. We introduce n here. N, the subscript, stands for normal component of the curl H. That means n is the unit vector perpendicular to the surface under consideration. Perpendicularity. So n represents curl H is only normal component, having normal component in this equation. So curl is always normal to the area under consideration. So delta is the area enclosed by the closed path C. So in this example, the delta S is delta X into delta Y. So I can replace the first term by curl H n after applying the limit. Similarly, the last term, that is I by delta S, is having a dimension of amperes per meter square. So it can become current density, but only after applying the limit delta S tends to 0. Then it becomes J. So it is required to apply the limit throughout, that is delta S tends to 0, to have some known quantities. And if I proceed in that regard, I'm applying the limit. Delta X delta Y tending to 0. So the first term becomes curl, last becomes the current density J. Middle term is independent of the area, so no change happens in the middle term. So we have an equation now. Curl H having only Z component. Why Z component? Because the area, what I said, delta S, is only having the two sides, delta X into delta Y. Okay. The perpendicular direction for this area is Z, A cap Z. So that's the meaning of that one, curl H Z. Similarly, current density is a vector, which is having the Z component in this definition. Similarly, we can write the equations for other components of the curl H, X and Y components, in the same way. Instead of deriving again using the concept of the Z component of the curl, we can write the same thing. You can see that one, curl Hz. These partial derivatives are changed here in the second and the third. Now I would like to combine all these three components of curl H, X component, Y component, Z component. The components are scalar values, you know that. So scalar value into unit vector will make them vectors. So after adding all the three, not only curl terms, we are adding these curl terms. Correspondingly, we are also adding other terms also. So finally, we get a relation this way. So all the curl terms are added. Similarly, the middle terms, partial derivatives are also added, and current density terms are also added vectorially. So in this step, what we can do, all these three components put together, I can write vector J. Similarly, all these three components put together, we can write curl H. But if you observe this middle term, the term with the partial derivatives, a careful observation, tells that these terms are the outcomes of the solution of a determinant. So what is that determinant? Look at this now. So now this determinant, after solving, will give us the result in the previous step. So this determinant solution is quite difficult to remember, but writing this determinant is very easy. We can solve it whenever we want to know the value of curl. Okay. So because of this determinant, we can write curl H as del cross H. We know that in the cross product, the first row is always unit vectors. Second row is the first vector in the cross product. Third row stands for second vector in the cross product. Dou by dou S, dou by dou by dou by dou Z are XYZ components of the del operator. So based on it, we can write del cross H. So the del cross H is this determinant itself. So in place of determinant, I can write del cross H. So we have the relation here, curl H is equal to del cross H is equal to J. So by writing separately, we have two useful equations. Curl H is always given by del cross H. Del cross H helps to evaluate the curl of magnetic field. Also, del cross H is equal to J. This is a very useful equation, and this gives the relation between the magnetic field intensity and current density. And this last equation is popularly known as point form of Ampere's law, or differential form of Ampere's law. It's also called Maxwell's equation. We shall discuss that part later. So we have derived a very useful relation, that is curl H is equal to J. So this particular derivation is discussed in rectangular coordinate system, but still is applicable to all the three coordinate system. So I'm giving you here the three possible equations of computing del cross H in different coordinate system. So del cross H in rectangular, in cylindrical in terms of R phi Z. See here R is there, multiplying the phi quantity, and 1 by R is dividing. These are the two changes we have to remember with respect to rectangular coordinate system. And in spherical, the whole determinant is multiplied by 1 by R square sine theta. Second term is multiplied by R, then R sine theta. Here, same thing here also. So we should know these changes over here. But here I'm giving you one more method of remembering this curl. So this is the generalized method of writing del cross H for all the three coordinates, not only three coordinates, any coordinate system for that matter. So that is del cross H equal to 1 by H1, H2, H3. H1, H2, H3 change from coordinate system to coordinate system. H1 A cap, H1 A2 A cap is 3 A cap. See, U1, U2, U3, they represent unit vectors. Dou by differentiation with respect to unit vector directions. Similarly, the components of H1. When you want to write del cross H for rectangular coordinate system, we can substitute H1 equal to 1, H2 equal to 1, H3 equal to 1. U1, U2, U3 are designated as XYZ. Similarly, by making these changes, corresponding changes, we can get those expressions what I discussed in the previous part. So remembering this one is quite easy compared to remembering three different equations for writing del cross H. So this completes the derivation for the point form of Ampere's law. Thank you.